Welcome to Module 6 in our series on artificial intelligence. This one provides an introduction to PyTorch as applied to machine learning. Now, what have we discussed in recent modules? In the first and second, we introduced the fundamentals of artificial intelligence, machine learning, and neural networks. In the third and fourth modules, we covered parametric modeling, including linear regression, as well as logistic regression. And in the last module, number 5, we applied a supervised learning algorithm to a basic, very basic, neural network architecture, a 3-input, single-output, single-layer perceptron. And focus was placed on binary classification using an error correction strategy. Let's provide a quick overview of the topics to be discussed in this module. Now, this module is all about PyTorch. What is PyTorch? It's an open source machine learning library developed by Facebook, or I guess now that's called Meta. It offers a flexible and dynamic framework for building and training neural networks. In practical terms, it provides software tools, so class objects like torch.nn.linear. We will discuss that in detail later on. So tools that automate many aspects of machine learning algorithm development, training, and testing. As a result, PyTorch is widely adopted by engineers and computer scientists for both machine learning research and production. Now, we're only going to be using PyTorch for the Python programming language, and that's the most popular way, the predominant way in which it's used, but I thought I should provide the caveat that there is some version of PyTorch available for C++, although I've personally never used that. The most popular alternative to PyTorch is TensorFlow, which we're not going to discuss here. They're both great options. Generally, PyTorch is considered to be better for research. It provides a little bit more flexibility, but it's not as efficient as TensorFlow. So TensorFlow may be preferred by industry for production-level designs, but both share many capabilities and features. So learning about PyTorch will definitely give you a leg up on learning more about TensorFlow and using that later on. Now, PyTorch represents data as tensors rather than arrays or matrices, but for the purposes of this module, these can largely be considered equivalent. We will talk more about tensors later on in this module, but it's not a focus here, and I don't want to get too lost in the weeds. One key advantage of using PyTorch over base Python along with NumPy, a numerical calculation library, is its automatic differentiation or auto-gradient capability. Each time PyTorch performs an arithmetic operation on or applies a function to a tensor, to some data, it also computes the derivative of the result or the output with respect to the input or certain designated parameters, both automatically and in parallel, hence the name automatic differentiation. Now, one note, you do have to turn on this auto gradient capability, so it's not always active. This gradient information is critical for machine learning techniques such as backpropagation and gradient descent, and they play a really important role in training. I know we haven't discussed these topics yet, but we will address them in future modules. Now, this module specifically focuses on translating the MATLAB Perceptron machine learning code, the one we developed as part of the last module. We want to take that from MATLAB and translate it to Python using the PyTorch library. And we're going to do this in 2 steps. So first, we translate the commands one for one, or as close as possible, and then we test this approach. Then, we reformulate and completely rewrite the script to take full advantage of important PyTorch features and capabilities, and before we perform this translation, we'll highlight what those features and capabilities are. The second step is especially important as it introduces PyTorch functions and development methods that are going to be employed for more advanced machine learning projects, both ones that you may see in the real world, as well as those that we're going to look at in future modules. Now, in this module, as most of our modules, we employ an example to demonstrate how this concept using PyTorch may be applied to a practical real-world problem. We're using the same example from the last module. We're going to employ both by hand and software-based calculations, although this very heavily skews towards software, and we provide QR codes and links to all the scripts so you can download them and play around with them at home. We also provide a homework exercise for you to attempt, and as always, our objective is to communicate practical and useful machine learning skills. So let's return to our main discussion on PyTorch, and the first topic that we want to discuss is the tensor. A tensor is an algebraic object that describes a multilinear relationship between other algebraic objects within a primal space while remaining invariant to change of basis. Now relax, this isn't a module on tensors specifically, so we're really not going to discuss at length what is a primal space, what is a change of basis. We can summarize the tensor as a structured set of numbers that defines some useful relationship, like a matrix. It's invariant to change of axis, referential directions, and/or basis, even though their components are not. The concept of a tensor extends our ability to describe and manipulate quantities within multi-dimensional spaces. But like I said, we're not going to discuss tensors, especially not the theory behind tensors at length here, but I do have an entire lecture series here on YouTube, as well as a textbook on tensors, so please check that out. The name of the text is An Introduction to Tensors for Non-Mathematicians, and you can see down here there are QR codes. One takes you to Amazon where you can purchase the book, and the other provides a free sample. So let's talk more about what a tensor means within the context of PyTorch. In this module, we're really going to use a more general definition of a tensor. We're going to assume standard and orthogonal basis sets and really ignore change of basis transforms. For that reason, I would really prefer the term tensor-like algebraic object, but we'll just call it a tensor. We're using the term tensor pretty loosely here. Now in this module, a tensor really just refers to some multi-dimensional or multi-rank algebraic object, something like an array as defined by the NumPy library. But unlike a NumPy-based array, a PyTorch tensor supports automatic differentiation as well as GPU acceleration, and we talked about what automatic differentiation was as part of the overview, and we'll discuss it briefly again. Here is an example of some Python code where we import the Torch library as well as create a basic tensor, a 2x2 tensor that contains 1, 2, 3, and 4. A tensor is the core data structure employed by PyTorch to store and organize data. One example would be synapse weights or training data, as well as build neural network-based models. PyTorch tensors, or really any tensor, can be classified in terms of their rank. So a rank 0 tensor or a rank 0 object would be a scalar. Here's how we can define a rank 0 or a scalar type tensor using PyTorch. It can be rank 1, and that would be an array. It can be rank 2, and that would be a matrix, as well as rank 3, and that would be a higher order object. And so here we have examples of creating an array type tensor as well as a rank 2 or a matrix type tensor. Now what about this 0 dim, 1 dim, 2 dim? Now PyTorch documentation we'll see often interchangeably uses the terms rank and dimension, which is an example that I'm not going to follow. So let's talk more about that. In this module, we use the terms dimensionality and rank very differently. Dimensionality, as far as how we use it in this module, refers to the length of an array or the number of elements contained within an algebraic object. So let's take the example of a three-dimensional space, right? We can use three variables, x, y, z, to define a location within a three-dimensional space. So we have a single array. It has three elements, height, width, and depth, and that allows us to define a location. So I'm going to refer to that as a three-dimensional object. Rank has a different meaning. It describes the total number of row and column indices required to index an element within an algebraic object. So for example, an array is just a list of elements, so we only need one index in order to determine which element we're looking at. If we had a matrix, right, we need two indices. We need a row number and a column number in order to indicate which element we're talking about. Now those indices obviously have to be positive, and the rank as well is always positive. We may also visualize rank as a positive scalar that reflects the number of spatial directions needed to represent the object on paper. Note that PyTorch documentation often uses these terms interchangeably, but we're going to try to be very clear here in the way that we use dimensionality and rank and make sure that they have two different and specific meanings. So here are some examples of rank 1, rank 2, rank 3 objects. I don't want to spend too much time on this, but just quickly, I wanted to provide a few examples. So a covariant rank 1 object is synonymous with a row-oriented array. It's rank 1, so we only need a single index to identify an element. Here we have a contravariant rank 1 or column-oriented array. Same thing, we only need a single index, but these are oriented as a column. A rank 2 matrix is shown here. We could also call that a covariant rank 1, contravariant rank 1 algebraic object. And for this, we need two indices in order to identify an element. The superscript, according to the notation that we use, the superscript index indicates the row number, and the subscript indicates the column number. So this represents the contravariant index, and this represents the covariant index. And then here we have an example of a rank 3 or a higher rank algebraic object, which is essentially a matrix. Right here you can see there's 4 elements shown, but each one of these elements has an array within it. So essentially, to index a single scalar within this algebraic object, you have to tell Python or whatever software you're using what row you're dealing with, what column you're dealing with, and then specifically what element within the sub-element you are looking for. Now, PyTorch, as I said a second ago, would simply refer to all of these as tensors, but we're going to go back and forth between using the term tensor and tensor-like algebraic object. Okay, now let's talk about a more relevant topic and get back to PyTorch. Why are tensors essential for PyTorch? And there's several key reasons here. One is flexibility. PyTorch facilitates fast and efficient transfer of algebraic objects as tensors between the CPU and the GPU, between the computer and the graphic processing unit. And so here's an example of a PyTorch command that allows us to assign a tensor to a specific location. Now, we're not going to talk too much in this module about the advantages of using CPU versus GPU. I think many of you are already familiar with those advantages, but hopefully that's something we can get to in a future module. Now, we've talked about automatic differentiation, so this auto-grad feature is important, and tensors provides that functionality. So PyTorch tracks how tensors are manipulated, multiplied together, added, squared, different functions may be applied. So let's say, for example, a natural log, and it automatically computes the gradients of all the intermediate values. Here's an example in Python of declaring a tensor with 2 elements and then telling PyTorch that this does require automatic differentiation. So it's also more efficient. It yields efficient mathematical operations. So PyTorch tensors facilitate faster, more parallelized communication. A lot of that has to do with the device flexibility and the ability to assign the tensors to the CPU or the GPU. And the tensors, or the PyTorch type tensors, are very relevant to real-world applications because we can represent any type of input, from a set of numbers, an audio file, an image, as a tensor, and we can also represent the outputs, whether that's a string of numbers or a prediction, such as that associated with a binary classifier. We can define all of those as tensors, so it's a very robust representation of data. Now, what are some important PyTorch tensor parameters or characteristics? One is the shape, and the shape represents the lengths of an algebraic object along its various ranks. So if we have a rank 1 object, an array, the shape is simply its length. For a rank 2 object, like a matrix, it can have a shape that's defined in terms of its height as well as its width. And if we had a rank 3 or higher object, then we would need the appropriate or corresponding number of lengths to define its shape. Another characteristic or another parameter is the data, and that defines the values contained within the object. Obviously, that's very important. Here we have several examples of how to define different tensors. Here we define a 2x2 tensor that contains zeros, a 3x3 tensor that contains ones, a 4x4 tensor that contains random numbers, a 3x3 identity matrix or identity tensor. And then here, we've shown a command like this many times throughout this module. We can define a tensor with custom values as well as a user-defined data type. Now, associated with that is another characteristic or important parameter of our tensor, and that is the data type. And so, pretty self-explanatory, it defines the type of data of the individual elements within the tensor. And you can refer to the PyTorch documentation to see what options are available, but it's the usual suspects: 32-bit floating point, 64-bit floating point, etc. Now, we've talked about the requires gradient characteristic previously, and so this tells PyTorch whether the auto-grad, the automatic differentiation capability, will be employed for a given tensor. And then we have the device characteristic, which tells PyTorch where the tensor should be stored, whether in CPU or GPU memory. Okay, so now let's get into the meat of this module, and let's begin converting our MATLAB code to Python using PyTorch. As we said before, we're going to be converting this existing MATLAB machine learning script from the last module to Python and PyTorch in 2 stages. The first one is to convert the commands one by one, or one for one directly. And this is going to use some PyTorch-based structures, and then we'll move on to stage 2 later. So the next few slides use a similar structure, where on the left-hand side we have the MATLAB script taken from the previous module. On the right-hand side we have the translated Python code or script that uses the PyTorch library. If you want to download the Python code, you can use the link here, the QR code. And if you want to download the original MATLAB script, you'll have to go back to the previous module and use that QR code provided there. Now, some of the commands have no counterpart between MATLAB and Python. One example would be the need to import libraries, which we don't do for MATLAB. So here you can see we import the PyTorch library, the NumPy library that provides some arithmetic and mathematical functionality, as well as this library that we use to plot or graph a couple of things. Now we begin by defining the maximum number of iterations that we want to allow for this thing to train, and we define a similar value over here. Now, I want to clarify before I start down this process that we're not going to spend too much time explaining the ins and outs of this code in detail. I think most of you that are familiar with software development, familiar with coding, for loops, familiar with using MATLAB, as well as hopefully a little bit of Python, I don't think this translation is going to be too difficult to understand. So we will fly through this pretty quickly. Now, in MATLAB, we defined the synapse weights as 4 different arrays, right? W14, W24, W34, and W04, with the final being the bias offset. In Python, what we did was define 2 different tensors. So tensor W stores the first 3 synapse weights, and then tensor W0 stores the bias offset. And so what you can see here is that we use a 32-bit floating data type for all of our tensors. And the way that tensor W is structured is that it's actually a rank 2 object. So what we can see is that going down, we have the iteration number, and going across, we have the synapse weight number. So what we expect is for the height of this to be the number of epochs, and the width of this to essentially be 3. And the reason why we want to do this is to have the ability to go back and look at the synapse weight value from previous iterations. Okay, down here we define a new tensor that I'm calling delta y, and this is simply going to be used to store the difference between the ideal and the estimated solution. And then we define our learning rate of 0.15. Okay, moving on. We define our training data set here as a matrix. Over here we do this as a PyTorch type tensor. We define a variable, which we're calling a Boolean variable. This convergence variable, we initialize it to 0, which is essentially telling the algorithm, the script, that we have not yet converged. We do something similar over here in Python. We then initialize a counter that I call KIT to 1, and this is how we indicate what iteration of the training process that we are working with. Now you'll note that for Python, we start with KIT equals 0, and the reason for that is that arrays in MATLAB start with 1, with index 1, and arrays in Python start with 0. And so we want to be able to use the KIT value to index these algebraic objects or tensors. We then ensure that the first training data sample is the 5th, and this is really going back to what we did previously when we were trying to match our hand-by-hand calculations. Over here, we set the initial training sample as 4, because again, everything is shifted down by 1, because the indices of the Python elements start with 0 and not 1. Still, same QR code up here in the top right-hand corner. Okay, now we start our iterative loop, right? That begins with a while loop statement. And what we're saying is while the Boolean convergence value is not equal to 1, same thing over here, right? We want to continue running through this loop. So here we choose an element from the training data set to use for the current iteration. And so for the first iteration, we want to use the 5th sample. We don't do anything, but if the KIT value is greater than 1, then we choose a random value. So we have a random number generator times the number of training data samples, and that's ktrain. So ktrain is the training data sample that we're using for the current iteration. We do something very similar over here, again using KIT and ktrain, the only difference being, the way that we implement the random number generator and the way that we quantify the number of training data samples. Okay, once we know what k-train is, right, what training data sample we want to use for the current iteration, we load the inputs and ideal output from the training data set. So you can see here we have k-train for all 4 of these values, and then we're taking the first, the second, the third, and the fourth elements and saving them as x1 for the current iteration, x2, x3, and then the ideal output. We do something very similar over here on the right using the same variable names. Okay, then what we do, shown in the purple, is we calculate the weighted sum of the synapse weights and inputs. And so we're using the W14, W24, W34 notation from MATLAB and multiplying it by these values here. We calculate the corresponding value on the right-hand side in Python, except we have to pull the synapse weights from the tensor W, and then we use those inputs that are saved. And then in this final part of the script, or almost final part of the script, we apply an activation function. So we're still using the unit step or heavy side function. Essentially, if the H value is greater than 0, we spit out a 1. If not, we spit out a 0. Same thing over here. We increment the iteration counter by 1, and then we use our error correction learning rule in order to update the 3 non-bias synapse weights, W14, W24, W34. Same thing over here. Now the only difference is for the MATLAB, we were just using those arrays inherently to track the values of the synapse weights. For the Python, what we have to do is store them or save them back to the 10W tensor that we were using to keep track of those values. And then finally, we check for convergence. And essentially what we do is we look at this delta y array. We look at the last 20 iterations or so. And if the value is very close to 0, in this case, we can say exactly equal to 0, but generally we don't do that. We would have a threshold that's very small. If it's equal to 0, we say convergence has been achieved. If the number of iterations gets above 48, then we also say that convergence has been achieved, although it's more appropriate to say that we've reached our stopping criterion. So down here, we can see the results that are yielded by the Python or the PyTorch code. And what we see is we end up with very similar synapse weight values, with the optimal value of W14 being 0.55, optimal value of W24 being 0.52, and the optimal value of W34 being negative 0.12. So if this doesn't make any sense, I recommend you go back and look at the solution yielded by the MATLAB code from the previous module, and you'll see that it's very similar to this. Now, where would you see this? This would be in the terminal window at the bottom of VS Code if you're using VS Code as your development environment. Okay, so let's ask a question. Why do we need a second approach? Why does this direct one-for-one code translation really kind of miss the point? Why is this approach suboptimal? There's several reasons. MATLAB and PyTorch, Python/PyTorch, they operate in fundamentally different ways. And the one-to-one or one-for-one translation ignores many of PyTorch's core features and benefits. So let's talk about some of those key differences. MATLAB, many of you, or hopefully all of you, are familiar with, is a highly flexible and generalized tool that allows us to solve a variety of mathematical and simulation-based problems, and that facilitates both numerical calculations as well as symbolic. Now, while it does support machine learning, especially through specialized toolboxes, and I don't want to minimize the capability of those, it's less tailored overall for large-scale machine learning projects. PyTorch, and I'll say Python and PyTorch, right, they facilitate faster and more scalable machine learning algorithm development, training, and testing because they provide users a specialized set of specialized data structures, one example being the tensor, with native auto differentiation capability as required for gradient descent, as well as, we've talked about many of these features previously, the ability to assign values to a CPU or a GPU. So there's a lot of advantages there. Now, this one-to-one or one-for-one code translation, right, ignores most of these benefits and these features. So what we want to do is look at a more optimal approach. One, again, where we regenerate the script from scratch using PyTorch conventions and better/best practices. And one example that we're going to talk about first is the torch.nn.module class object. So let's take a look at a more optimal implementation. like I said, the first thing that we want to talk about is the torch.nn.module class object from the PyTorch library. And so if you want to learn more about that, you can check out the Python documentation. I have a link in the top right corner. So torch.nn.module is the base class for all neural network modules. It represents a package within which our neural network can be constructed. Now, modules can contain other modules, and this facilitates greater complexity and the ability to use nested structures. And we use code, or we will use code, to demonstrate how we can implement a perceptron like this down here using the module class object. So we are going to demonstrate specifically how we take this picture, this diagram, and translate it to Python code. Now, another class object that we need to be familiar with is torch.nn.linear. Right? This class object applies a fine linear transform to the inputs supplied to a module. And we're going to use it within the torch.nn.module class object to define its forward propagation behavior, or essentially how it defines or generates outputs y based on inputs x. And it uses this weighted sum that we've seen many times before, right? This intermediate output, because we still have to apply an activation function, okay, is equal to the synapse weights times the inputs minus the bias. So the parameters of the linear class object are shown here. We have in features, or the number of inputs, out features, the number of outputs, bias, which is defaulted to true, and this indicates whether the machine learning algorithm will attempt to update the bias offset as a parameter, same way as done to the synapse weights. We don't always want to update this value. Sometimes we want this to stay the same. We have a device parameter, which defaults to none. Okay, and this tells the computer whether we want to perform various operations on the CPU or the GPU, and then the data type employed for the parameters of the linear class object. Now note, we still need to apply the activation function separately. All right, so now let's take a look or move on to examining the torch.nn.module class object example. So we are going to look at the code in its entirety in a second, but I wanted to start off with this skeleton, right? This outline of the code, so when we get to the actual script, we'll have a better understanding. So it can really be split up into two separate pieces, right? Within this class, which we call instantiate perceptron, that's based or derived from the torch.nn.module class object. The first is init, or instantiate, right? This instantiates the model structure, but it does not explicitly define the input-output relationship, and so you can see that code in blue. It contains a constructor, which facilitates the appropriate class inheritance, and then, probably more importantly, is it defines the model structure as a single weighted sum using the torch.nn.linear class object. So next, we need to talk about the forward functionality shown in red. Now, this does define the input-output functional relationship, and it can be split up into 2 or 3 parts. In the green, we see where we call the single neuron functionality, which is defined up here inside of the instantiation function, right? We call this in order to generate the weighted sum, right? And that comes from the use of the torch.nn.linear class object. And then the purple shows when we apply the sigmoid activation function to generate the output. And then finally, we return this output after the activation function is applied. We return that to the parent portion of the script. So here we have the full code without that coloring again. We're defining a class that is named instantiate perceptron that's derived from the torch.nn.module class object. It has 2 functions, the constructor as well as the forward propagation function. In the constructor, we have to tell it how many inputs it should accept, how many outputs it needs to generate. Right in this inheritance hierarchy, super, this command, is used within the instantiation or initialization method to ensure that it's properly created. And then here we define a neuron as an implementation of the torch.nn.linear class object with the associated number of inputs and outputs. And here we're also telling our model, right, that we don't want to apply the updates or the machine learning updates to the offset bias. So the offset bias will stay constant. Then Down here, we define the forward propagating behavior of the perceptron. So up here, we define the structure of our neuron, and down here, we define the input-output relationship. So we call the single neuron attribute, right? We define this attribute up above, we call it down here, we supply the inputs to it, it yields the weighted sum, we take that weighted sum, we apply it to the sigmoid function, as provided by the PyTorch library, it generates an output, which we then return. So that's the best I can do to try to explain this code. I think there definitely is an element of this, as there is with any coding example, where you are going to need to look at the documentation and sort of find your own way to understand this. So now that we've defined the instantiate perceptron constructor based on the torch.nn.module class object, we can go ahead and test it. And the easiest way to do that is to test the forward propagation, to supply it some inputs and see if it generates the output that we expect, and we can draw upon some of the values that we calculated by hand in the last module for verification. So let's do that. First thing we need to do is we need to define some synapse weights, or initialize, but in this case is really just define them. So we're going to call it 10W. It's a PyTorch type tensor, and we're supplying it these three values, 0.1, 0.22, and 0.03. Now these should sound familiar because they're the same ones we used from the previous module when we were performing this example by hand and implementing the error correction algorithm by hand. Okay, and it's a 32-bit floating number. Now, one thing we should note, and I think I've said this already, we cannot initialize the synapse weights when the automatic differentiation or autograd functionality is employed for training. So even though we can do that here, because we're just doing forward propagation, we'll see later when we put everything together that we'll no longer be allowed to do that, and PyTorch will make us randomly initialize those synapse weights. Okay, then we define the training data set, again, as a tensor, and a lot of this code could have come from the initial stage of this module where we did the one-for-one translation of the Python code or the MATLAB code to Python code. Okay, here we define the instantiate perceptron constructor, and so the reason why I have written previous slide is because that's all the code we have right here. That would go here. And then we actually instantiate the perceptron, right? So we create an object that I call my perceptron that we create using this constructor. It accepts three inputs, it generates one output, and it accepts these tensor values. Now, the one thing you may note is the way that we defined it here, it wasn't able to accept any synapse weights. So we had to change the code a little bit to allow it to accept these synapse weights. So the code of this version of instantiate perceptron versus the one on the previous slide, there's a couple small differences, but it's all with the purpose of generating this value of negative 0.04. If you remember, right, this was the weighted sum value that was yielded by the first iteration of the by hand calculations from the previous module. Anyway, so what we do is we call our my perceptron object, call the forward propagation function, and we supply it the fifth, well in this case fourth, but we're starting from 0, so the fifth training data sample. We get a summed weight of the synapse weights and the inputs and the bias offset of negative 0.4, and so therefore our final binary classification is a 0. Now, to make a long story short, all this shows is that 1, we're able to use the instantiated perceptron, and 2, right, it yields a value that we've already shown from previous by hand calculations, again with the assumption that we're using the fifth training data sample, we've already shown to be correct. So what's missing? We've spent a lot of time putting together bits and pieces of code in this module, but our goal ultimately is to recreate the same functionality, the same results yielded by the MATLAB script from the previous module. But in this one, what we want to do is we want to use Python and PyTorch, and we want to use the full capabilities, benefits, and features of PyTorch. So in order to complete that script, to complete our objective, there's 4 parts that we need to define, and we've already completed one of them, right? We've already defined our instantiate perceptron constructor, which is derived from the torch.nn.module class object, and this defines the model for this machine learning example, which is essentially a single layer perceptron that accepts 3 inputs and spits out a single output. But there's 3 pieces that are missing: 1, 3, and 4. The first is the header and the initialization, right? We need to import the appropriate libraries, define the learning rate and the maximum number of iterations or epochs, and define the training data. Now, most of this code was already present in the section where we tested the forward propagation, so we can just copy and paste that. The big missing piece here is the third, to actually perform the machine learning or to actually execute the training. And so there's several things that we need to do, several tasks we need to perform within that section. Specifically, there's 1, 2, 3, 4, 5, 6. Okay, this one is easy. I think we've already demonstrated code for that. We need to choose a random training sample and extract the relevant inputs and outputs. We did something similar in the first approach, the first stage, where we did a one-to-one translation of the MATLAB code to Python. We need to perform the forward propagation. We've already tested that, so we know how to do that. Then we need to calculate the error or loss, and for this we're going to use the mean squared error loss function. So at the end, we're going to talk about some differences between this implementation and the one from the previous module, but I will put off that conversation till then. We then perform back propagation and compute the gradients required for descent. I know we haven't discussed back propagation and gradient descent yet, but we will in a future module. We then perform a single optimization step, which updates our weights to reduce error. We check for convergence, and we keep going round and round until we reach a converged state. And then, once it's converged, we can test our trained model. All right, so what are some important PyTorch class objects, functions that we need to be familiar with for this code we're going to show, the training code? Okay, a couple of these we've already seen, right? The torch.nn.module, torch.nn.linear. These together define the model structure. The module is the base class, and linear facilitates the weighted sum of the parameters and the inputs. We have here torch heaviside and torch sigmoid. Those both can be used as activation functions. Heaviside is a simple unit step function, while sigmoid compresses those values between 0 and 1. Torch.optim.sgd is an optimizer. So this is new. I don't think we've seen this yet. It's an optimizer that updates model parameters using gradient descent. But one note, this really only instantiates the optimizer, and we have to use some other functions to actually execute the updates. The forward function, I think we're familiar with that. We've shown that before. It defines how the inputs propagate through a given model to generate the outputs, right? We supply 3 inputs x. It applies the weighted sum, an activation function, and spits out an output. We have the backward function. This calculates the gradients or the sensitivities of a model output with respect to its parameters as required for back propagation or gradient descent. And then the step function applies the updates to the model weights during the training. So this right here, this function is that which actually updates the synapse weights. And so hopefully all of these and their roles will become more clear once we look at the code example, which we're going to do right now. So it's not too long, which is nice. We start off with a for loop for our training, where our iterative variable is kit, and we are going to continue iterating until we reach a maximum value. Okay, next within the loop, we need to zero out gradients to prevent value accumulation. I'm not going to talk too much about that, but it's something that PyTorch recommends that we do, or the documentation recommends that we do. We then need to determine which training data sample will be used for the current iteration. We've talked about this code previously. Essentially, it defines a random number, multiplies it by the length or the number of training data samples, and then uses a floor function to essentially give us a number between 0 and 7. So for each iteration, it gives us a different sample within the training data set. We then extract the inputs as well as the ideal output for the current training iteration as stored within the training data tensor. We then execute the forward propagation, and we generate the estimated output, and for that, right, we call upon the myPerceptron object, which was built using the instantiate perceptron constructor, which was in turn derived from the torch.nn.module class object. Okay, we then have to calculate the error or the loss between the ideal and the predicted or estimated output. Now this function is defined elsewhere. When you download the full script, you can see it, but essentially what it does is it takes the difference between the ideal and the estimated, and it squares it. Okay, we then store this delta yk value to an array of length 10. Now why an array of length 10? We'll talk about that when we get to convergence in a second. So we check for convergence, so we're already there. Now how do we do that? What we're doing is we're taking the maximum of all the values within that array, and if it's less than a certain threshold, we break. So we keep cycling through all these values, storing our delta value in each spot. Once we get to the end, we circle back to the beginning. So in here is a record of the last 10 loss values, or the last 10 error values. So we look at the maximum, or look for the maximum of all the values in this array. If the maximum value is less than this threshold 0.01, we know that the error is small enough. Again, this is subjective right here, and we break, which brings us out of the for loop. Now, if we don't break, then we have to use the backward function to compute the gradients of the current tensor, right? The tensor, which is the error function. So we apply the backward function to the loss function, the error, not to the my perceptron itself. And then we simply step the optimization forward, and this is the optimization we defined up above. So the objective of this module was not to discuss PyTorch documentation in depth, as would be required to fully explain every aspect of this script. For example, what specifically does the optimizer do? Why do we call the step function as applied to the optimizer, but yet we calculate the gradients using the backward function as applied to the loss and not the perceptron? That's not the objective here. Okay, what our goal was or is, and what I hope we've been able to achieve, is to provide you with an overview, with a code skeleton, with an outline of the kind of script that's required to apply machine learning or to train a pretty basic neural network like the perceptron from the example in the previous module. So hopefully what you can do is take this example and extrapolate it. Extrapolate those lessons and apply them to more complex machine learning problems, whether those are ones you see in your work or studies or those that we're actually going to use in future modules. So you can download the full Python PyTorch script right here, and I highly encourage you to download it, try running it, and make some changes on your own. So these are the results that will be displayed. If you're running this in VS Code, it'll show it in the terminal window, and you can split it up into two sections. So here are the messages that show while it's running various iterations, and here's the results or the messages that it shows after the results are yielded. So what can we see? This is the message associated with the final iteration. That's iteration 3609. I know it took a lot more iterations than the script from the previous module, the MATLAB, and we ask about that as part of the homework exercise. And the final synapse weights that it yields are not exactly the same as the MATLAB, but they do follow a similar pattern. Two positive values with about the same magnitude, and then a negative value for the third synapse weight. Now down here, you can see the results, and there's 8 rows. So 0, 1, 2, 3. Okay. And in the blue, we are showing the outputs that are estimated or calculated by our trained neural network. And then over here in the green are the ideal values. So you expect these to be close. Now, they're not exact, right? Instead of getting a 0 for the first training data sample, we get 0.01. Instead of 1, we get 0.94. Instead of 0, we get 0.13. You get the idea. However, for binary classification, we'd normally be applying a threshold anyway, so any value less than 0.5 or less than some value would be a 0. Anything above that would be a 1. So if you did apply that binary classification filter to the blue data, the data shown in blue, you would get exactly what's shown in green. So although it's not the most efficient implementation, it does yield ultimately a correct result. Okay, so a couple notes here before we finish up this module. The second implementation, right, the one where we rewrote the code, uses gradient descent as its training strategy, rather than the basic error correction that we used previously in the MATLAB and in the first one-for-one code translation. Now, why? While PyTorch can support basic error correction, that functionality is not built into the class, so we would have had to implement it manually. So I chose gradient descent, to highlight PyTorch's built-in support for this type of optimization. Now, to support gradient descent, we had to make a couple other changes. We also had to modify the way that the error or the loss is computed, because we need for that loss function to always yield a positive value. So we used the mean squared error loss function that we learned from the logistic regression module. And if you look at the script, you can actually see where the mean squared error is defined. So in short, there are several differences between the MATLAB code and the one-for-one code translation. I packaged those two together. There are several differences between those and the PyTorch code we just looked at. The implications of those differences, will be a topic we explore in future modules. Okay, so let's talk about our homework exercise, which asks you to diagnose the inefficiency of the PyTorch training. So our PyTorch implementation required thousands of iterations to converge, whereas the original MATLAB version converged in just a few dozen iterations. So what I'm asking you to do is to identify the issue. Why does the PyTorch code stage 2 PyTorch code converge so slowly? Propose an improvement, modify or suggest changes to reduce the number of training iterations to fewer than 100, if possible, and you can consider changes to the learning rate, how initialization is performed, how loss is quantified, or the architecture overall. and then benchmark your fix. Record the number of iterations required before and after your change. So please post your solution, your proposed fix, and reasoning in the comments and the discussion section below. You can use Dropbox, Google Drive, or GitHub links to refer to code. And once we get a decent number of answers up in the discussion session, I'll go ahead and provide my solution. So let's go over a quick summary of this module. What was the objective of this module? To introduce PyTorch to you, and I think we achieved that objective, right? We talked about the most important aspects of the class and components that we need to use in order to implement a machine learning algorithm using PyTorch. So PyTorch is a powerful and flexible framework that enables us to develop and test machine learning algorithms with significantly less effort as compared to alternatives. Now, the amount of effort that we saved is probably not evident from this example because we're working with a very simple neural network, a perceptron that accepts 3 inputs and generates a single output. However, as we get into more advanced problems, to addressing more advanced problems where we may have tens, hundreds, thousands of inputs and a similar number of outputs, I guarantee that the efficiencies provided by a library like PyTorch or TensorFlow become absolutely essential. PyTorch provides high-level components, such as the torch.nn.module class object, for defining model architecture and efficiently handling tasks like tensor operations, addition, subtraction, multiplication, calculating gradients, and then optimization. These built-in tools not only reduce development time, but also make it easier to test and debug our machine learning simulations. As we continue through this module series, as we continue to discuss artificial intelligence, we will increasingly rely on PyTorch as our primary environment for machine learning development and testing. Really, from this point forward, I don't intend on using too much MATLAB, and I am optimistic that perhaps at one point we'll have an opportunity to discuss TensorFlow briefly. So the next topic here is listed as TBD because I'm not really sure what the next one will be. I'm working on several different modules in parallel. I think there's a strong chance that perhaps we'll be discussing automatic differentiation, gradient descent, and backpropagation in the next 1 or 2 modules.